presentation. Good luck.
Okay, thank you. Good morning, every one of you. Let me share my screen and then we'll start.
Please.
Thank you. So you can see my screen, huh? Every one of you?
Yes, we can
Is that
see.
okay? Okay. So Dr. Kifaya gave me little time because I have to rush for another presentation which is going to happen at 12. So without wasting time on the introduction, we'll start that what we have done is we have designed an effective optimized memory access mechanism for the embedded systems. This is me, Amala has done very nice introduction. So what we are basically doing is embedded systems, as we say that for IoT and drones and all the applications, we need to have on-chip computation, on-chip memory access, and that should be very fast and it should be in runtime. Uh, Normally what we do is off-chip computation is not a problem, but for on-chip, the delays that can create a lot of problem if you want to do a runtime decision. Imagine a drone flying at a speed of 300, 400 kilometer per hour, and with the image processing, it has to do certain decision and do something on that on the basis of maybe that's the security drone, any other ambulance drone or anything. So imagine that the time which that drone will have to decide for all of the aspects is too short. So that's the reason optimized memory access is something which is need of the day, and there are many mechanisms for memory accessing, register accessing and those things, so that you can make it faster. So again, the motivation is that microprocessor, all they have the cache memory. Again, the cache memory is because of the same thing that you want to do it as fast. You don't want to put it into off chip memory. You take it on the on chip memory. So there are two types of memories: on chip and off chip. On chip memory is on the processor, and off chip is the memory which we talk about the computers. So on chip memory, it gives high latency application as too expensive, because there is contention. You connect the memories, and there are different control channel, data channel, and the information channel. So they do some sort of contention in order to send the commands onto the memory bus. So number one, for with more computational complexity, when the computational complexity increases, it becomes more and more expensive, and it deteriorates the performance of the microprocessor. And the major constraint is the digital system is affected latency. Latency is something which is very important. And if you want to develop some algorithms for video, image processing, or an application of high data transfer and real time, then definitely we need a very high speed memory. So the background is the large number of memory access or data computation are expensive. Yes, we know that. You need to reduce latency. We need to reduce power of the system. And dynamic RAM and static RAMs, they are designed. But normally, all the memories, the initial algorithm is that the one instruction result is waited till the next instruction starts. And we do manipulate and play with these things. So the model which we have presented is it reduces the memory access latency, but on the other hand, it increases the cost of the system. But and that's basically understandable, because if you have parallel memories, they will increase the cost. So we increase the bandwidth, we optimize the latency, and we use the clock borders as well. So instead of having the clock level, we use clock borders as well to make the system more efficient. So let me just briefly and quickly explain the problem. There are certain commands like activate read 1, read 2, and this is simple chart which is showing that how we'll get the output after how many clock cycles. So activation is time 0 and 0, and there is a delay which is the command delay to execute, and then we will be having a clock cycle 3 and the total delay is 3, and we'll do read 1. Now this command also takes 5 clock cycles to come. So over here we are having 8th clock cycle, and 8 is the delay, total delay. And then if the delay is 5, then 8 plus 5 is 13, so we are having total delay of 13. So in order to execute these two commands, basically read 1 and read 2, we are going to have 13 clock cycles of delay. What if read 1 and read 2 are done in parallel? Again, this is a basic concept, we can do this. So there are three techniques: loop morphing, loop fusion and loop transformation. Both are doing the same thing, that if there is a loop, instead of running those loops independently, there's one technique which says that, okay, put in the loops in the bigger loop so that when the bigger loop is finished, all smaller loops are also finished. But again, there are certain pros and cons of that approach. The loop fusion is there are two loops, you just fuse them and make a bigger loop. And loop transformation is you change that loop and change the hierarchy of that loop. So the compilers, these three techniques, we are using all these three techniques for our research to have a better latency results for the system. So compilers are efficient to determine the memory access. Yes, we know this. Parallel processing, we have to do this. And loop transformations that fuse, they utilize the empty slots. So there are many slots which are empty, and then we utilize those slots. And these techniques are actually increasing the local accesses and decreasing the lifetime of the arrays. Again, if there are certain commands, and you'll see that in the next diagram, if there are certain commands and they are happening, there are two things which are happening over here. One is that they are taking some time, they are taking some clock cycles to complete. And the other one is there are some memory slots which are allocated for those particular registers, but those are empty. So we can manipulate both of them and do some efficient memory access. And then loop transformation limits the application to the loop technique, and morphing techniques is used to reduce the latency. So the morphing, this is based on fusing unconformable loop into a bigger loop, and it's an added advantage of the loop fusion. And attractive loop morphing for the memory bandwidth increase techniques, okay? And we have significant results with this loop morphing. Again, loop morphing is the same thing. One loop is the bigger one, the smaller one you put it inside, and you use the free memory slots in them and make the system so efficient that at the end of the day there is low latency, and all these commands are executed in quickest possible time. So existing delay model of DRAMs, the model systems, they do off-chip memory access. Again, there are two types of memory access. One is on-chip and one is off-chip. So for off-chip, this is something we are discussing, and result in increasing latency, because if from the cache or the register from the processor you have to go to memory, it will take time. And again, there is a computational complexity of the memory. So if you do some good modeling, and this is something in all the core processors we are seeing these problems, that when there is a more load on the processor stuck because it has to go to off chip memory, and we can access in multiple ways, and the performance of the system and reduce the latency. So the modern processors, they have problem of high latency. That means that if you deploy a chip 8 core or 16 core or 64 core processor onto a drone which is flying at a speed, or in the satellite or in the robots or something, and they have to make independent decisions, there is a possibility that if there is something which is called, in the neural networks we call it brain freeze, and it has to decide, it has to do some more computation, then there will be a delay, and that's the big problem at the hardware level. So again, because we are using the memory accesses, we are using multiple arrays, and in order to link those arrays through linked list, and managing this is something which is really intricate. And we need to schedule these arrays and allocate these arrays to appropriate memory modules to minimize the time. Okay, so our main focus is that memory access of operation in embedded systems and choose them effectively. So for example, if there are single operation that x0 is equal to y0 plus z0, so what we'll do is we'll read y0 first, then we'll read z0, and then of course we'll do computation and then write the value in the register x of 0. So this is a simple command read and write cycles, okay, simple assembly. And if you do them and use them in a proper way, so see, at the clock 0 we are activating, and this 3 is basically the read first command has to execute. So at this 3, if read 1 is executing, we are starting read 2 at 4. We are not starting read 2 at 3 plus 5, 8. So the delay is 8, but we are starting this at 4, and it has its own time, and it has the command delay of 5, but we are going to finish this at 5 plus 4, which is 9. So this is how we are increasing efficiency of certain command. Imagine there are millions and millions of these commands, and we do use certain algorithms for management of these memories. And then, so our technique, So we access the off-chip dynamic memory, and this can be scheduling and different factors, and the approaches are memory access algorithm, allocation, those things. I'll just show you what we have done. Uh, the objective of efficiently access the off-chip, again, is in its integration of the system, okay? And this can be done by scheduling of memory access. Number one, you schedule the memory access, how you access the memory. Allocation of the modules of the memory, which memory you are allocating to a certain things, and allocation of memory to modules. And these different factors need to activate it at the same time for efficiently. Again, the control fabric will be quite strong for this thing. And these three approaches are efficient memory access, appropriate allocation of memory modules, and use of advanced dynamic buffer. And then we'll see. So there is a recently adopted page mode techniques for the efficient access. Again, this is written in the paper. You can go into detail. I'll just quickly go to the results which we have. And other techniques like allocation of memories, assigning arrays to these memories, efficient binding and scheduling. Okay, that's fine. And dynamic methods integrated into a single approach. So these three methods we have done into a single approach to get good results. And once we do this, and when we do transfer video or image from the off chip, this is very, very fast. It has to be fast. But for our approach, we are reducing latency, but on the other side, it is increasing the chip area, and which is increasing the cost. But again, we can think of this and we can optimize this thing. So off-chip dynamic memories is scheduling the arrays, okay, and frequently accessing these large arrays of the memory. If you access them frequently, like there are multiple commands and multiple tasking and multiple cores are doing from processor to the off-chip memory, that there is something which is called memory. You do memory defragmentation, coalescing memory. So there are memory holes and free memories. So with the passage of time, it becomes inefficient. And that's the reason at some time our IT people, they suggested, okay, you need to restart your computer daily because that cleans the memory. That's fine, but you cannot restart a robot or a drone where it's flying on the flight. So we have to think on the on-chip and off-chip online memory management methodology. So again, multi-way partition technique, they are arranged efficiently for the reduction of the overall latency, and then efficiently arranging these arrays, we optimize this thing. And this approach that arrays group together depending upon the number access made to the off chip. So we group the delays. For similar tasks, we group those delays and we group those arrays and then do the tasking, and we have the visibility of the empty slots into that, and we use that. And basis of information access in the arrays is parallel. Okay, let's see. There's a spline cubic function, which is again a non-linear stuff. We solve it from point to point, point to point, and point to point. And there are certain operations which are being done. We have evaluated the processor on the basis of that. And then there are two types of algorithms which you do for the partitioning. For example, if there is a problem, then there's something which is called min cut and max cut. Min cut is you cut the tree in such a way that at least in every one they have the minimum of the computational complexity, while in max cut you cut the tree in such a way, again this is the graph theory, in such a way that you have the largest one over there. So what we have done, we have adjusted the value of regular line basis of information, so the regular lines which are the delays, and the first step is we had inverted the conflict graph values and then added new regular lines to the array to make it easy. Again, this is the implementation of the algorithm. And the second stage is to remove the existing line having the highest conflicts. So once we draw new lines, we remove the old high conflict lines. And the next important step is to adjust the value of regular line in the max cut. So in the max cut, we adjust the lines, and then we have an optimized graph on which we see, okay, how we'll manage. And partitioning the memory modules into two groups, we can resolve the conflict between two arrays. Let's see. So this is how. So if we cut over here, this is an architecture that different. The array B and C now store other memory modules. Okay, so B, C, they can store other memory modules. Once you cut this, so instead of making this much, we use these smaller graphs, and that's the reason we can increase the clock cycle performance. Okay. So second approach is latency through idle select time utilization. So what we are doing is we are using the idle. Yeah. Okay. So idle time slots are basically the other thing is we use the idle time slots for this thing. Again, I need to be fast because so here that will save. So these are different registers and they are basically connected to address data and control buses. They are communicating and you see that there are different operations. So and these different operations they are dependent on each other. So this is empty because this is waiting for some result. This is empty because this is waiting for some result. This is empty for because this is waiting for some result. And there are new writes and previous writes and new reads and previous reads. So we can exploit uh, these empty spaces and use certain things, certain loops within those empty spaces to make it efficient. And the third one is approaching partition of the graph in multiple ways. So I'll just go to the results. So this is how we have done. We have certain benchmarks, the processors, and the total number of arrays. In this case, we did it 4, and since it's a bigger processor, we can do it 15. Total number of conflicts we did is 3. Okay. Okay, are 3. And the conflict, if we do the min cut partitioning, one conflict is resolved and the cost is 2. If we use R operator, 3 conflicts are resolved and the cost is 6. So see, for the standard benchmarking in the min cut, we have compared this thing with the pure min cut. So we are resolving more conflicts, but this is causing, because of the scheme, because these are parallel arrays and parallel chips, that is increasing the cost of the system. And same is the case for IBM 2 and 3 and 15. One more thing we see, if they see in the vertical, that if their processor has less number of arrays, the 100% conflicts can be resolved. If the processors have more number of arrays, less of the conflict is resolved. So number of increasing the arrays, that reduces the efficiency, and that's understandable because and that's the reason we are under distributed computing and the cloud and everything, that you distribute this thing. But again, if you are distributing your memory access to certain clusters, you need to think that if you are getting a benefit of delay for using of the same memory, there is a communication delay between two clusters as well. We have to take care. And again, in Ericsson, I worked on some cloud system which has the backbone which has optical. So optical backbone, through that processing was electrical, but the communication between the processors are optical. So experimental results is the most frequently raised. There are two different ways in the scratch pad, and we have seen the improvement. We analyze the static and dynamic memory scratch pad and the application through array systems, and the most frequent use are array B, D, and E, and here we have the results. So we should show for maximizing the number of modules until all conflicts are resolved. So we should increase the module, reduce the array so that we resolve all the conflicts, and this will increase the chip area of the memory module and the efficiency of reducing the latency of enhanced source significantly. And the integration of all these three approaches using cyclic accurate delays, number 1. Number 2, model partitioning, and 3, memory into effective module and using the advanced dynamic memory, that good yields to the big result. So this we can see again the same table which we have done. When we do, this is something our latency, original latency of the clock cycles, and if we do the 3 approaches, this is, you see there are significant improvements in all of 3 4 benchmark processors. So conclusions, that we need to explore the ways to reduce the latency. This is important. Again, I'm saying this is important. Latency in the chip is important for whole of the IoT and whole of the virtuality and whole of the off-the-shelf, on-the-ground sensor applications. And you need to use cyclic accurate delays models. Okay, we did that, and we have the significant reduction over latency, and more research can be done so that you can reduce the cost as well or the size as well. And then research produce almost 9% is achieved as compared to the previously page model techniques. So I had to be fast. Thank you very much. So the crux of whole of this presentation is that there are different memory management techniques, and we have exploited the combination of those memory management techniques to reduce the delays. We were successful in reducing the delays, but on the other side, it increased the cost of the system, which we can do in future research. Any questions, please? Thank you very much.
Thank you, Dr. Asif. It was very informative. I felt like after sitting in my master's classes for microcontroller memory
and,
management,
and computer
after that, this
architecture,
is
yeah.
the first time I'm sitting and listening to a very detailed
Yeah.
presentation. I'm not an expert, but during that time, I was in love with microcontroller memory management, etc. And nobody could beat me. But now I envy you that you're working in that particular area.
Yeah.
Thank you, Dr. Asif.
Thank you.
So, are there any questions from the
From the
audience?
and I can be contacted anytime at my email or through Dr. Amala. Everyone knows it.
Yeah, I have one question. Can I ask
Yes,
Dr.
yes,
Asif?
please,
Because
please.
we have 3-4 minutes more.
Yeah.
Actually, you have come up with a very fantastic memory management system for embedded systems, which
Yeah.
is the need of this time. Did you compare with already existing embedded systems in, memory management
Yeah, we did
algorithms
that.
which
And
are there in the market? In
yeah,
what way yours will be unique that I can adopt yours?
yeah, again, I told you this is something we have compared this one with the existing one.
Yeah, I saw
Okay,
this
these are the
one, but
benchmarks.
then
These are the
you were quickly passing
yeah.
by.
So these are basically IBM benchmarks, and for all these three configuration, we have implemented this splint queue function, and we simulated our results, and we saw that this much improvement we have seen. And in the table we have the figures as well, that okay, for IBM 1 we use 4 arrays, conflicts were 3, resolved were 1. This is the min cut, which is the standard which is used, and that's the problem basically, and that's the problem in the embedded systems. And when we use our approach, this one resolved 1 conflict with min cut, and we resolved 3, but the cost from 2 to 6 increased. So for all these benchmarks, we have done the comparison through our simulation. So this works, but the only thing is it increases the cost and the size of the chip. So that since
That's
chip
what the
sizes are
next
depleted.
question I wanted to ask you addressed it.
Yeah. Okay, any other question? After 2 minutes, Dr. Summer is waiting for me for IoT.
Yeah. Okay, thank you so much.
Okay.
Audience, please note that I have again pasted the link and the title of the paper for you to fill up for the best paper criteria. Please, may I request you kindly click that link and put your inputs for Dr. Asif's paper research findings, please. Thank you, Dr. Asif.
Thank you.
Can you stop the presentation? So
I'm stopping, and I'll beg pardon to leave because I have to go to other session. Thank you. Thanks a lot. Thank you.
I do understand. I do understand clearly. Thank you so much for this.
Bye-bye.